it is me again. Blue Lake ASMR. And today we are still continuing, obviously, with reading the mathematics book Calculus by Michael Spivak. Today we are going to be solving problems from chapter 1. And what I have now done is I have pre-solved some of the problems so that I'm able to cover more problems in less time, because I don't have to spend so much time in thinking of the solutions of the problems. So, as said, the strength of this approach is I'm able to cover more problems in the same time. But then the drawback is that you don't get to really see my thinking process as clearly. But I'll still try to explain how I approach the problem, because I feel like just showing niche proof for some problem doesn't really teach you anything about the problem, but what teaches you is the journey and the process towards a solution. So I'll try to provide that. And I think let's open the notebook. Yeah, so we ended up on problem number 5. VIII. Should I call this VII or 8? Like I've been saying like VII, for example, because I feel like saying problem 5, problem 8 is misleading, because problem 8 is also here. But yeah, okay, but that is irrelevant. Let's get to the main part of this video. So let me zoom you in a bit. Problem 5. So, problem 5, part 8 says if A is greater than B, no, if A is greater than 0 and B is greater than A, and similarly for C and D, then we ought to prove that AC is less than BD. So let's try. So is first. Let's take the first premise. And multiply both sides by C. Then we get that because C is greater than 0, the inequality signs don't flip, and we get that AC is less than BC, obviously. And now we have the AC here, and we wanted to prove that AC is less than BD. So okay, we here have BC, and it is quite obvious to us that BC should be less than BD because D is greater than C, right? And well, turns out it's quite easy, because if we now take the first premise and multiply both sides by B, we get that BC is less than BD, and then this is already kind of the proof. Then you just chain these together and you get, as desired, AC less than BD. So again, following quite strict rules on what we are allowed to do, we were able to prove a quite elementary result. Now, I think we've done enough problems from 5, so let's try to move on to 6. In 6 we have parts A, B, C and D, and in each of those we are asked to prove something. Let's look at A. If x is less than y, both positive, then x to the n is less than y to the n. And well, this is intuitively obvious and luckily quite easy to prove with a lot of rigor. So let's take our notebook and turn a new page. Move the camera a bit like this. So we are given that number 6a, we have x less than y, both positive, and we want to show that x to the n is less than y to the n. And of course the main thing here is that they are both positive, which means that we can multiply by x or by y without flipping the inequality signs. So let's first multiply by x to the power of n minus 1. Multiply. So what do we get? We get that x to the n, we can add the powers together. At times x to the power of n minus 1. Yep. But then we need to somehow get y to the power of n on the right side. And well, it is kind of obvious that y times x to the power of n minus 1 is less than y to the n, but that would be quite a circular argument to use, as that is kind of what we're trying to prove. So let's try a different approach, a kind of inductive approach. Let's cross this over and just multiply by x, and we get that x squared is less than xy. And indeed, xy, using results from problem 5, well, for example, part 4 of problem 5, we find that xy is less than y squared. Okay, and then we can multiply again by x. We get that x squared, let's just forget this term and take this, is less than, no, x cubed, my apologies, is less than x times y squared. And again, using results from part problem 5, we find this is less than y cubed. And then we can continue doing this until n, to get that x to the n is less than y to the n. This obviously is not a super rigorous proof. But sorry about that. But it is very easy to make this into a rigorous proof just by using the principle of mathematical induction. But I won't do it now because that step is quite trivial. There is probably a simpler proof for this, but I couldn't think of one. If you can come up with one, please let me know. But now let's look at 6b. 6b asks us to prove the following. If x is less than y and n is odd, then x to the n is less than y to the n. So, what do you think? The point of this problem is obviously that so the big difference compared to number A is that x and y might be negative. X and slash or y might be negative, which means that if we multiply by them, we have to flip the inequality sign. But the trick here is that we are given that n is odd, which means that, well, x means x to the power of 1. So, to get to x to the power of n, we always multiply by x to an even power. And do you know what multiplying or what an even power means? An even exponent means that it's always greater than 0. So let's put b here. We are given x less than y. And now we can use the result from 6a. That if we have some elements greater than 0, then this holds. So let's pick, obviously x and y are not necessarily positive, but let's choose m such that 2 times m what am I saying? Yeah, so n, because it's odd, is 2 times n, 2 times m, where m is some positive integer, plus 1. And so let's take 2m is kind of the key to the solution here, because we can take this and multiply both sides by x to the power of 2m, and it is guaranteed that this is positive because it's an even exponent. So then we get that x to the 2m plus 1 is less than x to the 2m times y. And then, by similar reasoning as in the last problem, we conclude that x to the 2m times y is less than y to the 2m y, because again, even exponent means positive, and thus we get x to the n less than y to the n, because we defined 2m plus 1 to be equal to n. sketchy to me, but I think it should be okay. I know it's not the most rigorous proof, but it is still correct, I think. But don't take my word as always as a fact. I'm not even a mathematics student, so I might be wrong. Now let's look at problem C. Prove that if x to the n is equal to y to the n and n is odd, then x is equal to y. I'll move the camera a bit upwards. So we are given that oh, sorry, I don't see it. Can't see it. My setup is not perfect. It's very much homemade. My phone is resting on top of a chair or on the side of the chair, and a book is on top of my phone such that my phone doesn't fall down, and my microphone is on top of a stack of 5 books, so it's high enough for me standing on the floor. Not standing on the floor, sitting on the floor. But anyway, x to the n is equal to y to the n, and n is odd. That is n is 2m plus 1 for some integer m, non-negative integer m. And so let's rewrite this in terms of m. X to the power of 2m plus 1 is equal to y to the 2m plus 1. And now normal algebraic manipulation. Let's multiply. By x to the power of negative 2m. We get that x is equal to y to the 2m plus 1 times x to the negative 2m. I actually don't know how to continue from here. Maybe this is the wrong approach. So we have x separated on the left side. is of course again intuitively obvious. Why? It would be true, but a simple proof is hard to think of. Maybe we just move forward and come back to this at some point if we remember. So now let's move on to problem 7. It's on the next page. In problem 7, we are asked to prove that if AM is less than B, both being positive, then this kind of chain of inequalities holds. And let's do this one by one. First considering this inequality, A less than square root of AB. I'll first drink a bit of water. So let's open a new page in our notebook. And 7. We are given that A is less than B, both being positive. And both are positive, so let's multiply by A, not flipping any inequality signs. A squared is less than AB, and thus by just taking the square root we find that A is less than square root of AB. Quite simple. So the first part of the inequality is proven. Now to the second one. Square root of AB less than A plus B over 2. And well, this is quite a classic one. We start from the fact that any square is non-negative, so A minus B squared must be greater than or equal to 0, and thus A squared minus 2AB plus B squared is greater than or equal to 0. Now we add 4AB to both sides, getting A squared plus 2AB plus B squared is greater than or What is this? Does it look familiar? This is also a square. It's a plus b squared. Now let's take the square root. A plus b greater than or equal to square root of 4 times square root of ab. Square root of 4 is obviously 2, so a plus b over 2 is greater than or equal to square root of ab. And well, in the problem they ask for greater than, not greater than or equal to. And well, I should have already here mentioned that we don't need the equality case because we are given that neither a or b are 0, and thus this is never 0. So we can remove this and get the desired result. Remove this and get the desired result that a plus b over 2 is indeed greater than square root of ab. So I kind of enjoyed that proof. It uses kind of two observations, both relating to squares. And then off to the last part of the inequality. We ought to show that a plus b over 2 is less than b. Let's again start from the basic premise that a is less than b. And let's just add b to both sides. A plus b is less than 2b. And then just divide by 2 to get the result that a plus b over 2 is indeed less than b. So again, quite an easy proof. So in number 7, we proved this chain of inequalities, which is quite nice. Especially the middle inequality required some work, while the first and last ones were a bit simpler. Then I feel like number 8 did seem quite interesting to me, but not interesting enough to go through. So if you want, you can pause here and try it out. But I won't cover it. I can also quickly show and remind you of P10 to P12, which can be found here. We have the trichotomy law, closure under addition and closure under multiplication. But we are gonna move to number 9. Express each of the following with at least one less pair of absolute value signs. minus square root of 5 plus square root of 7. So, consecutive primes and their square roots. So we had number 9i, absolute value of square root of 2 plus square root of 3 minus square root of 5 plus square root of 7. And well, we have to remove the absolute value sign. And well, how do we do this? Well, we can notice that square root of 7 is obviously greater than square root of 5, which means that square root of 7 minus square root of 5 is strictly positive. Which means that we can separate these like this. Square root of 2 plus square root of 3, positive obviously, plus square root of 7. Oh, sorry, I didn't mean to write a bracket there. Minus square root of 5. And this is positive, this is positive. And thus this whole thing is positive. And thus we can just remove the absolute value signs without adding a negative on in the front. So we can just simply get square root of 2 plus square root of 3 minus square root of 5 plus square root of 7. Ta-da! Then there is 9ii, absolute value of a plus b minus absolute value of a minus absolute value of b. And well, I did try to think of this for a while, but just didn't manage to remove a single sign of a single pair of absolute value signs. But maybe I'll think of this a bit now with you and move on if nothing comes to mind. So somehow we have inside here a plus b inside absolute value signs, and then a and b separately. Absolute value of a plus b minus a minus absolute value of a minus absolute value of b. How do we remove a pair of absolute value signs? I know how. It is a known fact that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So we have the initial thing is this. And this can be written as absolute value of a plus b minus inside brackets absolute value of a plus absolute value of b. And by the triangle inequality, we know that this absolute value of a plus absolute value of b is always greater than or equal to this. And thus, this whole expression is always 0 or less, and thus we can remove the outermost absolute value signs. Sorry about that. And add a negative on the front. So it's minus sign, absolute value of a plus b, minus plus absolute value of b is equal to absolute value of a plus absolute value of b minus absolute value of a plus b. Okay, seems like sometimes I can solve things on video. Then the rest of problem 9 are kind of similar. Number 4, part 4 is done by just completing the square, finding this is always positive, and then you can remove the signs. And well, in here you kind of do similar things as in part 1, but I won't go into detail on those. But rather, let's jump to well, we have a problem here, but I find it quite disinteresting, especially because it even encourages you to do case treatment, which I just find kind of boring sometimes. So let's skip problem 10 and move on to problem 11, which asks us to find all numbers x for which, and then. So let's do the first one. Problem 11, part 1. Absolute value of x minus 3 is equal to 8. And well, okay, I just said I hate casework, but this is obviously casework, because there are two cases. Either x minus 3 is equal to 8, or x minus 3 is equal to negative 8. And thus we get two answers. That's quite simple. Then part 2 is otherwise the same, but with an inequality sign. And I'll also show how to do that. So part 2, absolute value of x minus 3, was it less than? Yeah, less than 8. Now again we get two cases. Oh, it dropped. Either x minus 3 is less than 8, or no, and x minus 3 is greater than negative thus x less than 11 and x greater than negative 5. Combining these, we get that x is greater than negative 5, less than 11. This is the answer. So that's how you deal with simple inequalities, including absolute value signs. And an interesting fact is that the number of cases grows exponentially with the number of inequality absolute value signs, I think. No, not exponential. Sorry, I'm thinking if I just gave you misinformation. Not disinformation, because it wasn't on purpose. Well, I think it is at least the case in inequalities. Because, for example, if we have something like x minus 3 plus x minus 4 equal to 8 with absolute value signs, then we would have to consider cases x greater than or equal to 3 and x greater than or equal to 4, x greater than or equal to 3 and x less than 4, x less than 3 and x greater than or equal to 4 and x less than 3 and x less than 4. And if we would add a third absolute value sign, this would again double. So yes, it does grow exponentially. It's 2 to the power of n, where n is the number of absolute value signs. But in this linear kind of absolute value equation, but obviously we can reduce some of these cases, or like remove some of these cases. For example, x is less than 3 and x is greater than or equal to 4 is never true. But the general idea of it growing exponentially is indeed true. I did not provide misinformation. And should I go through number 4, part 4, with 2 absolute value signs and inequality? Yeah, I'll do that. So I'll move this a bit higher up again. The phone like this. So 11 part 4 is absolute value of x minus 1 plus absolute value of x minus 2. When is this greater than 1? And how I was taught to do this in high school, was the following. Okay, this is like the visual way to do it. Let's just first draw a number line. And then let's mark the critical points. X 1 is a critical point because at x equal to 1 this absolute value function changes, because it goes from positive to negative, this part then. And then similarly 2 is a critical point. And now we have to split it into intervals. We split it into interval of x less than 1. Then we take interval in between and a non-inclusive interval greater than 2. And then we get these cases. The first case is x less than 1, and thus both this and this are less than 0. So we put a negative sign in front. And now it's just normal equation solving, inequality solving. Be careful with the signs though. Plus 3, right? Yeah. And thus minus 2x is less than minus 2. And thus x is greater than 1. But immediately we notice that this doesn't make sense. Here we are given that x is less than 1, but we find that x should be greater than 1. So this is rejected. Now let's take the case x greater than 1, less than, greater than or equal to 2, less than or equal to 2, greater than or equal to 1, less than or equal to 2. Now the first absolute value function is the insides are positive, so we don't put a negative sign in front, but on the second one we do. I just realized I made a mistake in the first part. This went to the wrong direction. Ching, 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 and ching. So in fact it is not rejected, but we get x less than 1, which matches perfectly with this. So whenever x is less than 1, this inequality holds true. Sorry about that. Someone there was probably screaming at me here for putting it the wrong way. But I'm just a human. Make mistakes. I'm just a human. Don't put a chain on me. That's the song by Rackbone Human, or something like that. was rejected. Then let's look at the last case. X greater than 2. Then we can just remove the absolute value signs. And we don't add any additional minus signs. So we get that 2x minus 3 greater than 1, 2x greater than 4, x greater than 2, which again matches perfectly. It doesn't need to match perfectly, but notice it does. So our answer is x less than 1 or x greater than 2. All of these values which satisfy with either one make this inequality true. Now let's turn the page, still continuing with problem 11. If you look at VII, so part 7, x, absolute value of x minus 1 times absolute value of x plus 1 equal to 0. For this, it can look intimidating. You're multiplying two absolute value functions together, but it's super easy because it's enough if one of these is 0. So either x minus 1 is 0 or x plus 1 is 0, and thus obviously x is equal to 1 or x is equal to negative 1. And the last one I do not know how to do. I guess some casework, but I can't be bothered. So let's move on to problem 12. First one is asking us to prove that absolute value of xy is equal to absolute value of x times absolute value of y. And well, I feel like my methods are not like rigorous enough, but how I would just do this is, okay, we have absolute value of xy, and I would say that it is obviously equal to absolute value of x and absolute value of y, because it's anyway gonna be positive, so it doesn't matter if we add absolute values inside. And now we don't need to alter absolute value of signs, and we get the desired result. I feel like that's a bit cheating, but whatever. In the first video I think I emphasized a bit too much how important it is to be rigorous, because now I feel like I'm not being rigorous enough. But let's move on. Also, I feel like it is a bit. At first, I felt this a bit mysterious. The best way to do this is to remember what absolute value of x to the power of minus 1 is. But I feel like I figured out what he meant. and this is how I would do it. So we are given absolute value of 1 over x, which is equal to absolute value of 1 times x to the power of negative 1. And well, using part 1 we can separate these. And this is just 1, so we can ignore it in multiplication. And this is equal to and well I can, this is so low level to me, but like the only thing I would do is just move the power above, because, and my reasoning here is that a power, an odd power especially, well no, any power in general cannot make a thing negative. So it doesn't matter if it's inside or outside the absolute value signs. This feels again a bit like cheating, but I can't come up with a better way of doing this. Then, well, part 3 follows nicely from part 2. And part 4 annoys me. It is a trivial inequality. And it says, give a very short proof. And by this I mean I assume don't do case work or separate cases. But I just can't come up with a way to prove this. So well, okay, I guess if we are allowed to use the triangle inequality, then we could do that. We choose x and negative y, and thus by the triangle inequality this is true. Okay, this is probably what he meant by give a very short proof. Okay, funny, already twice I've been able to come up with the solution on the spot, and I think it goes to show how sometimes it's got just good to distance yourself from the problem for a while, and when you come back you suddenly realize the obvious. Let's move on to problem 13. The maximum of two numbers, x and y, is denoted by max xy. Okay. And then he gives us formulas for x, max xy and min xy. And he wants us to prove that these are true. And well, of just explaining, but I feel like this is quite self-explanatory anyway, because it's just a constructed thing. We just divided it into two cases. First, assume x is greater than or equal to y. Then, this absolute value sign, we get a negative on the front, which means that these y's cancel out, and we get 2x over 2, which gives us x, which means that if x is the greater element, this works. And similarly, if y is the greater element, we don't put a negative sign here, and thus the x's cancel out. We get 2y over 2 equal to y, and it works. And that's my proof. And I feel like that's the obvious and only way to do it. I won't even write it down. But it is still kind of a nice formula. I myself am a programmer. At first I thought, ingenious, I'll stop using the max and min for max and min functions, because they are slow and stuff like that. But no, and this is much faster because it's just scalar addition. But no, first of all, max and min functions are quite fast. They just do a simple comparison, and this is just the same. This is not really a formula. Like, sure, we are just adding scalar elements, but we still have a comparison, because the absolute value, it is inherently just a comparison. So no, I won't start using this in my programming. But if you want to confuse someone by your program, then you can use this instead of min-max. Yes, I was thinking whether I should continue, but I feel like I'll end this video here, and in next week's video try to finish with the problems from this chapter. So I thank you for watching. I hope you found this video pleasant and educative. I'm trying to all the time kind of increase the quality of my videos. For example, I feel like the audio wasn't the best in the first two videos, so now I'm speaking a bit closer. So if anyone is watching, please let me know if you have any ideas for improvement. So thank you and bye. Yes, I was just showing off my